students. Today we shall learn about an important branch of spectroscopy called Raman Spectroscopy. And in that we shall see what is Raman effect, how do you explain Raman effect according to classical theory, and how we explain it using quantum theory. Now, about Raman spectroscopy. It was the Indian scientist Sir C.V. Raman, Sir Chandrasekhara Venkata Raman, who first observed the Raman effect experimentally in 1928. It was discussed theoretically earlier, but the first experimental observations were done by Sir C.V. Raman. And for that, he won the Nobel Prize in Physics in 1930. Now, Raman spectroscopy is the spectroscopy of Raman scattering. In this, we learn about the behavior of atoms within molecules and about the molecules themselves also. Now, Raman scattering occurs only when the molecule is polarizable, that is, only for polar molecules. And we study the spectrum in the region of visible light. Visible light is used to study about the Raman scattering. Now, Raman spectroscopy gives information which is similar to what is obtained in microwave and infrared regions. That is, when we radiate or excite the molecules using visible light, the molecules, they rotate and they also vibrate. That is the similarity. And because of that rotation and vibrational motions, we get energies from that. And that energy spectrum lies within the visible spectrum. Now, we understand that Raman scattering is an optical analog of Compton effect. What happens in Compton effect is high energy electrons, they bombard on molecules or atoms and they get scattered. And by studying the scattered electrons, we learn about the cross section of absorption of that molecule or nuclei. Likewise, here, white light, visible light, or in particular nowadays, lasers are allowed to fall on the sample, and the scattered light from that sample is studied. Hence, we call Raman scattering as the optical analog of Compton effect. Now, about Raman effect. In this picture, we can see light of energy E naught is incident on a sample, a molecule. And this sample can scatter light in different ways. The scattered light will contain components of the incident light itself. That is called the Rayleigh scattered light. The energy of the Rayleigh scattered light will be equal to that of the incident light. Now, the scattered light also contains components having lower energy than that of the incident light, and that is the red line showing here. So that is the Raman scattered light, and the scattered light also has components having higher energy than that of the incident light, represented by the blue line. They are also called the Raman scattered light. So let us look into it. Now, when a beam of monochromatic light of frequency nu naught, so the incident light is of a particular wavelength, it is monochromatic, its frequency is nu naught. When it is incident on dust-free transparent liquids like benzene or toluene or carbon tetrachloride, etc., light is scattered. And in that scattered light, most of the scattered light is transmitted without change in frequency. That is, the frequency of the scattered light nu will be equal to the frequency of the incident light, nu naught. Some of the scattered light has frequencies nu equals to nu naught plus nu m, and some of the scattered light has frequency nu is equal to nu naught minus nu m. So the light with frequency nu naught plus nu m will have higher energies. It is represented by the blue ray here. And the light with lower frequency nu naught minus nu m will have lower energies according to the relation E is equal to h nu. So if frequency is lower, energy is lower, and that is represented by the red ray having energy lower than E naught. So here nu m is the characteristic frequency of that particular molecular system. So each sample has a characteristic frequency. Now the scattered radiation with change in frequency, either increased frequency or decreased frequency, that scattered radiation is called Raman scattering. And Raman scattering is a weak process. Its intensity will be low. This inelastic scattering of light by the molecule that contains information about the molecular system is called Raman effect. Now let's look into the Raman spectrum that is formed. So this figure on the right shows the nature of the Raman spectrum. So at the exact center of the spectrum, we have the frequency of the incident source light used because that is reflected as the Rayleigh scattering. And on either side of that particular frequency, we have the Raman lines. Here in this spectrum, it is plotted against wavelength. So the higher frequencies, they are represented by the lower wavelength lines, right? And they represent the anti-Stokes Raman lines. Whereas the lower frequencies, that is higher wavelengths, are represented by the lines on the higher wavelength side. They are called the Stokes Raman lines. Let us look into it. Now, in the spectrum, we have three types of lines. First one is the radiation transmitted without change in frequency. That is nu is equal to nu naught. It represents the Rayleigh line at the exact center of the spectrum. Now, the unmodified line occurs with no change in frequency from that of the source light, nu naught. Its frequency is not changed. Then, it is a very intense line. Its intensity is very high. And then it lies at the exact center of the Raman spectrum. Now, the next type of radiation is the radiation scattered with frequency nu equals nu naught plus nu m. And this is represented by the anti-Stokes Raman lines. Now, these Raman lines lie on the higher frequency side of the Rayleigh line. In other words, in terms of wavelength, they lie on the lower wavelength side of the Rayleigh line, that is here. Now, they are less intense and less in number compared to Stokes lines. The intensity of these lines are less, and the number of lines may also be less compared to the other Raman lines. Then the spacing is symmetrical about nu naught. The spacing of these lines from nu naught is symmetrical. Now the third type of lines is radiation scattered with frequency nu equals nu naught minus nu m. It represents the Stokes Raman lines. Now these Raman lines lie on the lower frequency side of the Rayleigh line. In other words, in terms of wavelengths, they lie on the higher wavelength side of the Rayleigh line. and they are represented by these lines. Okay. Now these Stokes-Raman lines are more intense and more in number compared to anti-Stokes lines. Yes, the intensity of these lines are higher compared to the anti-Stokes-Raman lines. And the number may be also more. Spacing of these lines is symmetrical about nu naught. Again, the spacing of these lines from the Rayleigh line is symmetrical. Now let us compare between the Raman scattering and Rayleigh scattering. Now, Rayleigh scattering is the scattering of radiation without any change in frequency by the molecules that are smaller than the wavelength of the source light. Whereas Raman scattering is the scattering of the radiation with change in frequency by molecules smaller than the wavelength of source light. Now, in Rayleigh spectrum, the frequency of the incident radiation alone is observed. Only that central frequency is observed. Whereas in Raman spectrum, new lines of different frequencies are observed along with the incident frequency. So we have new lines here. In this spectrum, it is given Raman shift by wave number. 1 by wave number is equivalent to wavelength. So we have the Stokes lines on this side and the anti-Stokes lines on this side. And we have thus new lines of different frequencies. Now the intensity of the strong Raman line is 1 by 1000 times of the Rayleigh line. Now the intensity of these Stokes or anti-Stokes lines is just 1 by 1000th of the Rayleigh line, whereas the intensity of the Rayleigh line is 1 by 1000 times of the incident line. The intensity of this Rayleigh line is 1 by 1000 times of the intensity of the incident source light. Now let us try to explain Raman effect using classical theory. In that, we need to learn about the polarizability of the molecule and the induced dipole moment mu and the applied electric field E. Now here, this blue sphere, it represents a molecule and it is placed in zero electric field. So its positive and negative centers are not shifted. The positive and negative centers, they coincide and they do not have any resultant dipole. Whereas when the molecule is put into a static electric field, it suffers some type of distortion. That is, the positively charged nucleus, it is attracted towards the negative pole of the electric field, and the electrons are attracted to the positive pole of the electric field, and hence this molecule is distorted. Its positive and negative centers are distorted and they move away, and hence they form a induced electric dipole, and they have an induced electric dipole moment. Now, the size of this electric dipole moment, it depends on the magnitude of the electric field and the ease with which the molecule can be distorted. It means the nature of the bond of this molecules. Hence, the induced electric dipole moment mu is given as alpha into E, where alpha is the polarizability of that molecule. Now, let us understand about polarizability of a molecule. Polarizability of a molecule is anisotropic. It is not the same in all directions of the molecule. It is different in different directions of the molecule. Now consider the hydrogen molecule as such and let electric field E be applied in the direction perpendicular to the bond length. Here, the electrons forming the bond, they are not easily displaced by the electric field that is perpendicular to this bond axis. The bond length is not much distorted in this way. Hence, we say that this molecule has least polarizability in this orientation. Whereas, if hydrogen molecule is placed in such a manner that the electric field is parallel to the bond axis or bond length, the electrons of forming that bond are easily displaced by the electric field. Okay, and hence we say it has greatest polarizability in this orientation. Now, to define this polarizability, we make use of the polarizability ellipsoid. Let us see how it is defined. Now, the polarizability of a molecule in different directions is conventionally represented by drawing a polarizability ellipsoid. Right. By defining it, we have where the polarizability is least, the axis of the ellipsoid is greatest. And where the polarizability is greatest, the axis of the ellipsoid must be least. So in general, the definition of polarizability ellipsoid is that it is a three-dimensional surface whose distance from the electrical center of the molecule is proportional to 1 by root alpha, where alpha is the polarizability along the line joining a point on the ellipsoid with the electrical center. Assume that this molecule has an electrical center and it has the polarizability alpha here due to the positive center and alpha here due to the negative center when an electric field is applied here. Now, this ellipsoid, it is a three-dimensional surface that represents the polarizability in such a way that the distance from the electrical center is proportional to 1 by root alpha. Okay, so in this direction, we have the greatest polarizability. Hence, 1 by root alpha implies that the distance in this ellipsoid should be minimum. Again, in this direction, the polarizability is least. It implies the distance is proportional to 1 by root alpha, that is, the distance should be maximum. And hence, we have this axis as the maximum. Okay, so the minor axis represents the direction in which polarizability is greatest, whereas major axis represents the direction in which the polarizability is least. So with this ellipsoid, we can define the polarizability of a molecule. Thus, in this ellipsoid, the ellipsoid axis is proportional to 1 by root alpha, where alpha is the polarizability of the molecule. Now, let us move into the classical theory. When molecules are subjected to a beam of radiation of frequency nu, the electric field experienced by each molecule will vary according to the equation E equals E naught sine 2 pi nu t. Since the applied electric field is an EM wave, it is varying with the frequency nu. The molecule also experiences a varying electric field given by E equals E naught sine 2 pi nu t. Now the induced dipole moment given by the expression mu is equal to alpha E is written as mu equals alpha into E naught sine 2 pi nu t. So the induced dipole moment is also oscillating according to the frequency nu. Now this is the classical explanation for Rayleigh scattering. For this induced dipole moment of the molecule, since it is oscillating periodically, it gives light in the particular frequency nu itself, and hence it scatters light in the frequency nu itself, and hence this explains Rayleigh scattering. Now, while this molecule is oscillating, the dipole oscillating molecule, it emits radiation of its own frequency, its own characteristic frequency, right? Hence, the molecule, if it undergoes some internal motion like vibration or rotation while it is oscillating, it will change the polarizability periodically, and this leads to Raman scattering. So the oscillating molecule or the oscillating dipole will have uh, superimposed upon it the vibration or rotational oscillations also. And hence we have the change here in the polarizability. So we rewrite the term alpha as alpha naught plus beta sine 2 pi nu vibe into T, where alpha naught is the polarizability of the molecule when it does not have any vibration or rotation, and beta represents the polarizability of the molecule when it has additional vibration or rotational oscillations. And the frequency of the vibration or rotation will be nu vibe. And thus the induced dipole moment given by the relation mu is equal to alpha E will become mu is equal to alpha naught plus beta sine 2 pi nu vibe t into E naught sine 2 pi nu t. Now here we see a product form of sine A sine B form. So by the trigonometric expression sine A sine B is equal to half of cos A minus B minus cos A plus B. We rewrite this term mu is equal to alpha naught E naught sine 2 pi nu t plus beta into sine 2 pi nu vibe t into E naught sine 2 pi nu t, as mu is equal to the first term alpha naught E naught sine 2 pi nu t plus half of common terms beta E naught into cos 2 pi nu minus nu vibe t minus half of common term beta A naught cos 2 pi nu plus nu vibe t. Now, the first term represents the Rayleigh scattering because it is having the frequency nu. This represents the Rayleigh scattering. The second term, it contains the frequency of nu minus nu vibe. That is, the frequency is in the lower side. And this represents the Stokes lines. And the third term represents the oscillation having frequencies of higher side, that is nu plus nu vibe. And this represents the anti-Stokes lines. Thus, this is the classical explanation of Raman scattering. Hence, in order to be Raman active, a molecular rotation or vibration must cause some change in the component of the molecular polarizability. That is, when light is incident on the molecule should have an additional rotation or vibration that also creates a change in the polarizability of that molecule. Also, the change in polarizability is seen as a change in either the magnitude or the direction of the polarizability ellipsoid. Now, let us try to explain Raman effect according to quantum theory. So in the earlier times, we had the classical theory in physics, whereas under the light of quantum physics, we get to explain all the physical mechanisms, phenomena under quantum theory. So let us see how Raman effect is explained using quantum theory. So when light is incident upon a molecule, the incident light consists of packets of energy called photon. So photons are incident on the molecule, and the molecule scatters the light, scatters the photons in three ways. Some of the photons, most of them have the same energy as that of the incident light, and they represent the Rayleigh scattering, whereas the other photons have different energies than that of the incident light, and they are called the anti-Stokes lines radiation or the Stokes lines or radiation. Let us look into it. Now, when radiation of frequency nu naught is incident on a molecule, the molecule is excited to the upper quantized states. Okay. And the molecule interacts in three different ways. Now, in the first way, the molecule may merely scatter the photons without absorbing any of its energy, and that is represented by the Rayleigh line. Now, in the second way, the molecule may absorb a part of the energy of the incident photons and scatter radiation with frequency nu equals nu naught minus nu m. This represents the Stokes-Raman's lines. And in the third way, the molecule in the excited state, which is already excited due to the incident light, it may give away, it may impart its energy to the incident photons and scatter radiation with higher frequency. That is nu equals nu naught plus nu m. That represents the anti-Stokes Raman lines. Now, the Rayleigh line is a result of elastic collisions, whereas the Raman lines are a result of inelastic collisions. So here we see that in Rayleigh scattering, when light is incident on the molecule is excited to the higher energy states, and that same light is scattered from it when the molecule de-excites. Whereas in other cases, when the molecules are excited to upper excited states, they may de-excite to the higher lower levels. That means it may not be de-excited to the exact ground, it may be de-excited to the first quantum vibrational level. And that represents that lower energy is scattered away. That shows the Stokes-Raman lines. Now, in other cases, the molecule may already be in higher vibrational quantum levels, and from there they are excited to the upper quantum levels, upper energy levels in the visible spectrum. And when they are de-excited from that level, they de-excite to the lower vibrational zero quantum level, and hence higher energy is scattered or emitted from it, and this means that its frequency is higher, and it is represented by the anti-Stokes Raman lines. Hence, let us move into the explanation of Raman effect in quantum theory. Now, according to the principle of conservation of energy, the intrinsic energy of the molecule and the kinetic energy of the molecule before collision, along with the energy of the incident radiation, they must be equal to the intrinsic energy of the molecule and the kinetic energy of the molecule, along with the energy of the scattered radiation after collision. In other words, let us write it down mathematically. Here, in this expression, we should understand that the energies before and after collisions are equated according to the principle of conservation of energy. So when light is incident upon a molecule, that molecule will have a particular internal energy, plus the molecule will have the uh, kinetic energy, or the energy with which the molecule is moving. Okay, so when all these energies will be before collision, when light is incident upon it. So after the process, when light is incident upon it, what happens is the molecule's internal energy might change, the molecule's kinetic energy might change, and the energy of the scattered radiation will also change. So equating these two factors, we have E naught, the internal energy of the molecule, plus half mv square, its kinetic energy, plus h nu naught, energy of the incident radiation, is equal to E prime plus half mv prime square plus h nu prime. Now, these collisions, they do not increase the temperature of the sample. So then the kinetic energies of the molecules should be the same before and after collisions. It implies that E naught plus h nu naught is equal to E prime plus h nu prime. Now rearranging in terms of nu prime, we have nu prime is equal to nu naught plus E naught minus E prime by h. Now this represents the Rayleigh line and this represents the Raman lines. So here, when there is no change in the intrinsic energies of the molecule, that is E naught is equal to E prime, we get nu prime is equal to nu naught. And this represents the Rayleigh line. Whereas when there is a gain of the intrinsic energy of the molecule, that is E naught minus E prime is equal to minus delta E, we have nu prime is equal to nu naught minus delta E by h. And this represents the Stokes-Raman lines. Now, when there is a loss of intrinsic energy of the molecule, that is E naught minus E prime is equal to delta E, we have nu prime is equal to nu naught plus delta E by h. And this represents the anti-Stokes-Raman lines. Hence, this was the quantum explanation of the Raman effect. That's all for today's session. Thank you.